Let's do this problem again. But this time, instead of breaking it down by looking at the individual values of our charges and voltage on each capacitor, let's solve this by taking the approach of the equivalent capacitor. So in this alternative solution, I'm going to redraw our circuit. We have our power supply being labeled by Casai at 60 volts. We have our two capacitors in series, capacitor C1 and capacitor C2. This is essentially going to be the same diagram as we did before. So let's label this as charge Q1 and charge Q2. Let's also, while we're at it, go ahead and label our nodes. Here is A at the negative terminal of the battery, B at the battery's positive terminals, and C a node in between the two capacitors. We are going to replace these two capacitors with a single equivalent capacitor, which we will call C12. And C12 is going to have an equivalent charge of Q12. Now, with this equivalent capacitor, the only nodes that we have to worry about in this redrawing in the circuit are nodes A and B. The EMF of the power supply is still the same. Our goal is to find the capacitance of capacitor 2. Now, we could use the fact that capacitor 1 and capacitor 2 are in series, and we know that the equivalent capacitance of two capacitors in series is equal to the reciprocal of the sum of the reciprocals of each of the capacitances. Well, we could rewrite this as 1 over the equivalent capacitance is equal to 1 over the capacitance of capacitor C1 plus 1 over the capacitance of capacitor 2. Our goal is to find the capacitance of capacitor 2, and to do that, we would need to know the equivalent capacitance, and from that, subtract the reciprocal of the capacitance on capacitor 1. Well, just to continue fleshing out what we know, we do know what capacitor 1, the capacitance is. It is 12 microfarads. So since we know C1, we now have to determine what the equivalent capacitance is of the capacitors 1 and 2 combination. And to determine that, I'm going to use our acronym Valley College is Quaint. That acronym helps me to remember that the potential difference of our equivalent capacitor, that's the Valley part, times the capacitance of our equivalent capacitor, that's the college part, is equal to the charge on our equivalent capacitor. That's the quaint part. Valley College is quaint. Well, we know what the potential difference is of our equivalent capacitor because we know the potential difference from A to B. If we look at our equivalent circuit and go from point A to point B by passing through the battery, we see that the potential difference from A to B is equal to the EMF of the battery. Now, we can get to B from point A by passing through the equivalent capacitor, and we would see that the potential difference again from A to B, which is the same thing as the potential difference across the equivalent capacitor, must be equal to the same Casai. And the reason why? Potential difference is path independent. Whether we go through the battery or through the equivalent capacitor, the potential difference is going to be the same. And since the potential difference is going to be the same, from this diagram, we could see that the potential difference of our equivalent capacitor is the same as the potential difference across the battery. So we now have one thing that we need to determine our capacitance of the equivalent capacitor. Now let's determine the charge on our equivalent capacitor. Well, remember, for capacitors in series, the charge of the equivalent capacitor is equal to the charge on each of the plates, or the magnitude of the charge on each of the plates of the capacitors that are in series. And since capacitor 1 and capacitor 2 are in series with each other, the magnitude of the charge on each of their plates is the same. So that means the magnitude of the charge of our equivalent capacitor is the same as the individual capacitors. And we were given that to be 450 microcoulombs to be the charge on capacitor 2, which is the same as the charge on capacitor 1, which is the same as the charge of our equivalent capacitor. So now that we know the voltage across our equivalent capacitor and the charge on our equivalent capacitor, we could determine the equivalent capacitance. So the equivalent capacitance is just the ratio of the charge on our equivalent capacitor to the potential difference of our equivalent capacitor, which is equal to the ratio of the charge on capacitor 2, which is what we're given, over the EMF of the battery, Psi. So now we know the capacitance of capacitor 2, or of the capacitance, rather, of the equivalent capacitor between capacitors 1 and 2. We could use that to find the capacitance of capacitor 2. So I know to find the capacitance of capacitor 2, what I'm going to do is I'm going to get the common denominator between these terms on the right side. And when I do that, I get the difference in the capacitances between capacitor 1 and the equivalent capacitor over the product of capacitor 1 and the equivalent capacitor. I then take the reciprocal of this. When I take the reciprocal of this, this gives me an expression that allows me to find the capacitance of capacitor 2. Now, notice if we were to do just a quick unit check on this, I see capacitor 1 is going to have units of the farad, the equivalent capacitor has units of the farad. In the denominator, we have units of the farad for both terms. Farads cancel. Our units check. So I feel that algebraically, we probably got it. Since our units check, let's go ahead and plug in numbers. So the capacitance of capacitor 1 is given as 12 microfarads. Actually, before I plug in numbers, let's go ahead and break down the capacitance of the equivalent capacitor, because we know the capacitance of the equivalent capacitor is the charge on capacitor 2 over the EMF of the battery, as we found up here. So in using that relationship now, we have the product of the capacitance of capacitor 1 times the ratio of the charge on capacitor 2 over the EMF of the battery. And this is divided by the capacitance of capacitor 1 minus the ratio of charge to EMF that we're given. And now we have about everything we need. What I'm going to do, though, algebraically, I like to make things a little bit cleaner before I plug in numbers. So what I'm going to do is I'm going to just multiply the numerator and the denominator by the EMF of the battery. What that allows me to do is in the numerator, write the product of the charge on capacitor 2 times the capacitance of capacitor 1. And in the denominator, that allows me to write the product of the EMF of the battery times the capacitance of capacitor 1 minus the charge of capacitor 2. Okay, so at this point, I'll be satisfied with plugging in values. So the capacitance of capacitor 2 is equal to the product of the charge on capacitor 2, which is 450 microcoulombs, times the capacitance of capacitor 1, which is 12 microfarads, divided by the product of the EMF of the battery, which is 60 volts, times the capacitance of capacitor 1, which is 450, not 450, 12 microfarads. And it looks like I forgot to put my units of coulombs up in the numerator, so let me go ahead and insert that. And then this is minus the charge on capacitor 2, which is 450 microcoulombs. When we plug this into our calculator, we get 20 microfarads. And notice, this is the exact same result that we got up here by approaching this circuit in a different way. This first solution, we approach the circuit by looking at the potential difference across each capacitor, finding the potential difference on capacitor 1, because once we found the potential difference on capacitor 1, we were able to apply that to determine the capacitance of capacitor 2. So that was one way of solving it. And this alternative way that we just solved it was by relying more on the equivalent circuit. So we said that we knew that two capacitors in series can be represented by an equivalent circuit. And that equivalent circuit tells us some information. It tells us the charge on our equivalent capacitor, for one, and it gives us a relationship between the equivalent capacitance and the capacitances of the individual capacitors. By using that information, we're able to determine the capacitance of capacitor 2. So there's multiple ways to pet a cat, as my wife and I like to say. So there's multiple ways of doing a problem. As long as we are logical and consistent, each of these ways is equally valid.